In this lesson, we use an EEMBC automotive trace to analyze instruction side cache behavior. We are told that 70% of reads hit in L1, 20% miss L1 and hit in L2, and 10% go all the way to the last level cache or main memory. Our task is to propose a micro-op cache or instruction cache change that cuts instruction side misses by 30%, and then estimate the IPC gain, both mathematically and graphically. First, let us visualize the baseline instruction fetch path. We fetch instructions, check L1 instruction cache, then L2, then the last level cache or main memory. We will place the percentages on the diagram so we can reason about where time is going. To cut I side misses by 30%, a highly effective approach is a micro-op cache. This cache stores already decoded operations for hot loops and frequently executed traces. On a hit, the front end bypasses instruction fetch and decode, eliminating pressure on the L1 instruction cache. We will place a micro-op cache next to the branch target path, so after a predicted target, we probe the micro-op cache first. If it hits, we deliver ready to execute micro-ops immediately. We will assume a modest design, 1.5 kilo entries, 8 ways set associative way prediction, and 4 to 6 micro-ops per cycle delivery. Let us translate the goal precisely. The instruction side miss fraction, which is L1 misses, is currently 30% because 20% go to L2 and 10% go further to last level or memory. We target a 30% reduction in that miss fraction. That means the new miss fraction is 70% of 30%, or 21%. We will assume the reduction applies proportionally to the L2 and last level paths, so 20% becomes 14%, and 10% becomes 7%. The 9% saved now show up as micro-op cache hits that bypass the instruction cache path. Let us compare distributions visually. On the left, the baseline, 70% L1 hits, 20% L2, and 10% last level or memory. On the right, the new distribution adds 9% micro-op hits and reduces L2 and last level to 14 and 7%. This chart makes the improvement intuitive. Now we estimate IPC gain. We use a simple CPI model. Total cycles per instruction equals base execution CPI plus front-end stall CPI from instruction misses. To be realistic, an out-of-order core overlaps a lot of latency, so we use effective penalties, not raw latency. Assume base execution CPI equals 0.8. Assume an effective penalty of 2 cycles for an L2 served instruction miss and 8 cycles for a last level or memory served instruction miss. These effective penalties reflect overlap and prefetch benefits. Compute baseline first. Front-end stall CPI equals 0.2 times 2 plus 0.1 times 8, which is 1.2. So baseline CPI equals 0.8 plus 1.2 equals 2.0, and IPC baseline is 1 over 2, or 0.5. Now compute after micro-op cache. Front-end stall CPI equals 0.14 times 2 plus 0.07 times 8, which equals 0.84. Total CPI equals 0.8 plus 0.84 equals 1.64, so IPC becomes about 0.609. The speedup is baseline CPI divided by new CPI, roughly 1.22 times, or plus 22% in IPC. As an alternative, an instruction cache change can also cut misses by 30%. For this EEMBC automotive code, conflict and capacity misses dominate hot loops. Options include doubling associativity with a small victim buffer, modestly increasing size, or adding a simple next line prefetcher for sequential basic blocks. Any of these can deliver a similar 30% miss reduction and near identical IPC benefit under the same effective penalties. Finally, let us build an intuition graphic. We draw 2 front-end timelines. The red gaps are instruction fetch stalls. After the micro-op cache or better instruction cache, those gaps shrink. That shrinkage is exactly the 30% reduction of the miss fraction we calculated, and it maps to the 22% IPC gain under our assumptions. Recap: we began with 70% L1 hits, 20% L2, and 10% last level or memory. We proposed a micro-op cache that captures hot loops and reduces instruction side misses by 30%, which shifts 9% of traffic to micro-op hits and proportionally reduces the L2 and last level paths to 14 and 7%. Using a simple yet realistic CPI model with effective penalties, we estimated an IPC gain of about 22%. An alternative instruction cache tweak can produce a similar benefit for this workload.